use of groups and subgroups? We must know. Let's know the history of subgroups and groups. The original motivation for a group theory was polynomial equation of degree 4, and the 19th century French mathematician Évariste Galiléus, extending the work of P. Ruffini and J. L. Lagrange, gave a criteria for the solution of polynomial equation in terms of symmetry group of its roots. The elements of such group correspond to permutation of roots, which were investigated by A. L. Cauchy. Now, I am showing you the slide in which Galiléus and Klein are shown. Who was Klein? He gave the application of group in geometry. Geometry was a second field in which symmetry group were used as part of Flex-Callan's program. The third field contributing to group theory was number theory. So, my dear students, don't feel that way that a group is only a pure mathematical term. So, every day, everywhere we are using this group theory. Group theory can be appreciated by the science students in molecular symmetry, space group and symmetry in physics. The possible manipulation in Rubik cube form a group. You know what is Rubik cube? Let me show you Rubik cube. You must be playing with it. So, and an ammonia 3D or hexacube or cubecube or octave, all these scientifically used diagrams for group theory, where group theory is used. So, now shifting to what are groups, what is the definition of groups. Groups are a set. What kind of set? It is a non-empty set. So, this can be any kind of set. Let us consider a set of integers. Let us consider a set of integer where we are taking from minus infinity to infinity. Do you know what are integers? 0, 1, 2, 3, minus 1, minus 2, minus 3. We are taking the set of all those numbers. So, a non-empty set together with a binary composition. Binary composition is an operation like plus, minus, multiplication. We are denoting it by star. It can be any kind. Is said to form a group. In binary composition, if we are adding two elements, then the third element also belongs to that set. So, so if we are talking about binary composition, it means closure property is satisfied here. That is, the addition of two elements is again a element of the set. So, a non-empty set G together with a binary composition star is said to form a group. It is a group. So, a set, a non-empty set along with some operation or function or mapping denoted by star is a group, all right. So, integers are a group with plus sign. Let us set of integer is G with binary composition plus is said to be a group if it satisfies three postulates. What are postulates? Assumptions, three conditions. The first of all is associativity. Associativity means grouping. We can group, take 1, 2, 3, 3 numbers of the set of integers, all right. We can group 1 plus 2 first, then plus 3, then 1 plus 2 is equal to 3 and 3 plus 3 is equal to 6. Again take 1 and plus group of 2 and 3, then 2 plus 3 is 5 and 1 plus 1 is 6. So, in both the cases, the way, whatever way we are grouping it, it is same. So, associativity means we can group it either A star, B star C, that is equal to A star B, star C. So, firstly we are grouping B and C, and secondly we are taking together A and B. Then that means it is satisfying the property of associativity. So, set of integer is satisfying the property of associativity for all 1, 2, 3 belongs to the set of integers, or here for all A, B, C belongs to G. Now, what is the second postulate? Second postulate is the inverse and identity. First of all, we are taking existence of identity. Now, in case of integers, 0 is the identity. How come 0 is the identity? Like you can add 0 to 3. 3 plus 0 is equal to 0 plus 3 is equal to again 3, where 3 belongs to our group of set of integers, that is G. So, existence of identity means there exists an element E belongs to G such that A star E is equal to E star A is equal to A for all A belongs to G. So, E is then called identity, like 0 is in case of set of integers is called the identity. Next property is existence of inverse. Inverse, here when we are taking 1 in case of integers, then minus 1 is also existing in the integers, then 1 plus minus 1 is 0. So, it means for each and every element of that integer, we can find out its inverse such that their addition is identity. So, existence of inverse means for every A belongs to G, there exists A dash belongs to G depending upon A such that A star A dash is equal to A dash star A is equal to E. That is 1 plus minus 1 is equal to minus 1 plus 1 is equal to 0. So, then A dash is called the inverse of A, or in example case of integers, minus 1 is called the inverse of 1. Now, these after all discussing all the 3 properties of group, now the closure property which must be satisfied in group case, that is already satisfied because we are talking about binary composition. So, star here is a binary composition on G, or plus in case of integer is a binary composition. So, for all A, B belongs to G, A star B is a unique member of G. I gave the example earlier also that 1, 2 belongs to G, then 1 plus 2 is equal to 3 also belongs to G, that belongs to the set of integers. So, this property is called closure property. So, closure property is also satisfied. 4 properties: associativity, then identity, inverse and closure properties are satisfied. Then we said that if a group with binary composition star, if a set of integers with operation plus satisfies these 4 postulates, then it is a group. Now, to make it a abelian group, it must satisfy additional property of commutative. If in addition to the above postulate, G satisfies the commutative law, that is A star B is equal to B star A for all A, B belongs to G. In case of integers, 1 plus 2 is equal to 2 plus 1 for all 1, 2 belongs to G, then G is called an abelian group or a commutative group. Alright, we can name it also a commutative group or an abelian group. So, I hope you are aware with what is group now. Now, next shifting to finite and infinite group. If I talked about a set of integers from minus infinity to infinity, so you can't count the elements of that set, then it is an infinite set. But if you are taking a set like minus 1 to 1, then it is a group of 2 elements only, then the set is finite group. So, if the set G is finite, then it has finite number of elements. So, it is called a finite group, otherwise it is called infinite group. Clear? So, next we are going we are taking up some example. Let's first of all define order of a group. Order of group means number of elements in a group, that is always denoted by OG or G with bars. So, order of group is number of elements in a group. Let us take up one example. Just now I have explained that set of integers with infinite elements is an infinite abelian group. Now take the example of set of G of all nth roots of unity, where n is a fixed positive integers, forms an abelian group under usual multiplication of complex numbers. So, we know that complex number z is an nth root of unity if zn is equal to 1. Is z raised to power n is equal to 1, and there exist n distinct roots of unity. These roots are given by e raised to power 2 pi iota r over n, where r varies from 1 to n. Now, to show that is a group, let us find a finite abelian group. To show that it is a finite abelian group, we form a composition table by taking the fact that a n is equal to 1. Start with multiplication, and because a n is 1, we are taking 1 to a n minus 1. Again, secondly, we are taking 1 on the vertical side, 1 to a n minus 1. Again, we are taking 1 to a n minus 1, 1 to a n minus 1. So, similarly, we are completing the composition table. Then, now we will satisfy all the properties of a group. If AB belongs to G, be any two members of G, then AN is equal to 1 and BN is equal to 1, because Zn is equal to 1. Then AB raised to power n will be AN BN. Now, AN is 1, BN is 1. So, this implies AB is the nth root of unity. That satisfies the closure property, that if AB belongs to G, then A into B is also a member of G. So, next, associativity of the multiplication of complex numbers is always true, because whenever you are grouping complex numbers in either way, it is always true. All right. Then next, taking the identity, we know when we multiply A with 1, then it is always A, and A with 1 with A, it is always 1. So, 1 will be the identity in case of multiplication, and also if A belongs to G, then 1 over A also belongs to G. How? 1 over A raised to power n is equal to 1 over A raised to power n. So, A n is 1. So, that means 1 over A raised to power n is 1. So, 1 over A belongs to G. So, it means for each member of G, there exists 1 over A which belongs to G. Commutative being obvious, we find G is an abelian group. How commutative is obvious? Because we can group complex numbers either way, does not matter, like taking 3 plus 4 iota, all right, plus 6 plus 8 iota. Then the result will be same, or we can take 6 plus 8 iota plus 3 plus 4 iota. So, that does not make any difference. So, taking up another example, let G is equal to set of plus minus 1 plus minus iota plus minus j plus minus k. So, define product of on G by user multiplication together with I square is equal to j square is equal to k square is equal to minus 1, and ij is equal to ji minus ji, sorry, ij is always equal to minus ji is equal to k, and jk is equal to minus kj is equal to I, and ki is equal to minus ik is equal to j. Then G forms a group. We will prove that G is not abelian group as I is not equal to gi. So, this type of group is called quaternion group. Here, if we are taking I j k with 1, with all plus minus sign, it is a group, but it is not abelian group because of the property of ij is not equal to gi. Taking another example of matrices, if we take the set of all 2 cross 2 matrices of the form A, B, C, D over reals and AD minus BC is not equal to 0, there is a mistake, AD minus BC forms a non-abelian group under matrix multiplication. In this case, what will be the identity? 1 0 0 1. So, matrix 1 0 0 1 will act as an identity, and the matrix by the method of finding the inverse, we will find out the inverse of the A, B, C, D, that will be D over AD minus BC minus B over AD minus BC minus C over AD minus BC and A over AD minus BC, that will be the inverse. So, we have inverse and identity of the matrices, and we know matrices are having the property of associativity in case of addition, associativity and commutativity. So, associativity and closure property. So, it is a group, but it is not abelian group. Then next example is group of residues. Let G is a set of 0, 1, 2, 3, 4. We are taking a set of 5 elements. Then define a composition plus 5. That means we are dividing the sum of 2 elements by 5 on G by A plus B divided by 5 is equal to C, where C is the least non-negative integer obtained as remainder when A plus B is divided by 5. For example, 3 plus 4 is 7. So, 7 is divided by 5, it means remainder is 2. Then 3 plus 5, 1 is equal to 4. When we will divide it by 5, then 4, it will the remainder will be 4. So, this kind of composition where A plus B divided by some number and that is equal to remainder, we call it addition modulo 5, addition modulo 5. So, A plus B divided by 5 is equal to C. C is a remainder here, and this is called addition modulo 5, and the what is the binary operation here? Plus 5, all right, addition modulo 5. Binary composition, what is binary composition here? Addition modulo 5, we are taking G with addition modulo 5. Then taking up this example of addition modulo 5, we can generalize it. Then G also forms a group. When we generalize the group, the set from 0 to n minus 1 under addition modulo n, rather than 5 we are taking n, in is any positive integer, then A plus B, A addition modulo n B is equal to A plus B if A plus B less than n, and A plus B minus n if A plus B greater than or equal to n. This group is generally denoted by Zn. Now, after taking up the examples of group, we will shift to subgroups. What are subgroups? As the name explains, these are the subsets of that group. Like we are taking a set of integers from minus infinity to infinity. If we take up a small group or small set of integers from minus 8 to 8, then it will be a subgroup, because again it forms a group. So, a non-empty subset H of a group. First condition is of for any group is that it should be a non-empty subset. H of a group G is said to be a subgroup of G if H forms a group under the binary composition of G. So, any subset of G is subgroup if itself under that binary composition it is a group. Obviously, if H is a subgroup of G and K is a subgroup of H, then K is a subgroup of G also. Got it? If H is a subgroup of G and K is a subgroup of H, then K is a subgroup of G also. And if G is a group with identity element E, then subset E and G, if G is a group with identity element E, then the subset E and G are called trivial groups, trivial subgroups of G, and we call them trivial subgroups. These are trivial subgroups. What are the trivial subgroups? G itself and E, and all other subgroups will be called non-trivial or proper subgroups. Alright, G and what are the trivial subgroups? Only G and E, and all the subgroups which are proper subgroups are called non-trivial subgroups. Sometimes we use the notation H less than equal to G to signify that H is a subgroup of G. And when we are talking about proper subgroup, then we eliminate equality and H is less than G to mean that H is a proper subgroup of G.